So let's get going. So in the last lesson, we were playing around with trig functions. And these are the basic functions that I'm sure most of you have observed for, in the last 2 years. But I just want to point something out to you. If we look at these graphs, the sine graph is positive from 0 to 90. It's positive from 90 to 180. It's then negative in the next 90 degrees, and then it's negative for the next 90 degrees. The cos graph is positive initially, then it's negative, and then in the last 90 degrees, it's positive. And if we look at the tan graph, it is positive, then it's negative. If you look from 90 to 180, then it's positive, and then it is negative. Now, this is the behavior of the basic trig functions. What does this remind you of from another part of trigonometry? Where else have you seen this sort of patterned behavior when you talk about trigonometry? Yes, Lomelo, it is the cast diagram. Exactly, Cartesian plane, where we say, if we think of the different quadrants, so quadrants 1 to 4, and we think of our angles being 0, 90, 180, 270, or we could go the other direction. We think of that all the functions are positive in this quadrant. And you can actually see this in the graph. And then in quadrant 2, only sine is positive. And you can see that there. In quadrant 3, only tan is positive. And in quadrant 4, only cos is positive, which is here. And so it's nice to know that the cast diagram is really just another representation of trig graphs. They're related to each other. So that's one thing I want to point out. I want to ask you another question before we get going today. If I ask you, what is the value of the tan of, solve that trig equation for me. So tan of x equals 1, and you can just look at the tan graph to do that. So you don't even need to use your calculator, just look at the tan graph below. What do you know the value of, how do you solve that equation using just this graph here? So a lot of students are saying that x is 45 degrees, and you can actually see this on the tan graph. That 45, and if you put in your calculator, the tan of 45 gives you 1. Okay, so you've got that idea. Now, without using your calculator, what would be another answer for x for this equation? What other value, when you say the tan of this value gives you 1, if you were looking at your trig graph? I think you guys have got this, right? So if you look at what 1's in line with, 1 is in line with that value over there. And so you can say that another solution to this is 225. And if you put the tan of 225 in your calculator, you will indeed get 1. And what this shows us is something that we knew already. We knew that to solve a trig equation, there isn't just one solution. There are many solutions because trig graphs repeat themselves, or we say they're periodic functions. And when we look at the tan graph's period is 180 degrees. So it reoccurs every 180 degrees. That's why if you add 180 to 45, you get the next solution. Okay, so trig graphs are periodic, they repeat. But if we look at the tan graph, it is a period of 180, but the cos graph or the sine graph, they have a period of 360 because they have a slightly different shape. If we look, actually, let me just check. Thumbs up if that all makes sense. Thumbs down if I'm losing you on those basics. I just want to make sure I connect the cast diagram to the graphs and explain why the tan graph has a period of 180. The basic reason is that the tan graph is made up of actually the sine and the cos graph, and that gives it this funky shape. But if you want to just observe it, can you see that the graph repeats itself entirely every 180 degrees? So if you go from 90 to 270, that's one whole tan graph. And then the next whole tan graph is the next 180 degrees. And before that is, so the tan graph just repeats itself every 180 degrees. That's why we say the period is 180. Now, if we look at the cos graph, it has to go through 360 degrees before it starts repeating itself again after that. And then it just goes like this again. Then it'll be like the next. And so that we say that that's 2 cycles of the cos graph there. And so these are some trig basics that we want to just keep coming back to, reminding ourselves of. Let me zoom in for a second on something like, yeah, well, you can see the same thing with the tan graph, right? So the tan graph, it takes 360 to go through one full cycle. And if you carried on going, okay, and you kept on going and you want to come down again here, that would get you all the way to 720 for the next cycle. Actually, it should have actually, sorry, I should be going up once, down, down, up. And then that will give me the 4 quadrants, or the 4 pieces that get me up to 720. Okay, so that was the bit of revision. Now, let's talk about tonight, what we're going to do. So tonight, we are going to talk about what if I change the graphs in 2 particular ways. The one way is a vertical shift. The other one is an amplitude change. So let's start with the graph y equals sine x plus 1. And if I want to draw that on the domain 0 to 360, how do I do that? And before I show you how we can do this, I also want to ask you, what is the step size for this graph? Well, it's just going to be the period of the sine graph divided by 4, which is 90. Now, what I'd like you to do is I'd like you to take out your calculator if you've got one, because I'm going to show you how using your calculator, you can make drawing trig graphs a whole bunch easier. So let me see if I can share my screen. Give me a thumbs up if you can see a calculator alongside the question I've just asked. Because once you know how to use your calculator effectively, life gets very easy for trig graphs. Okay, so I'm going to do this slowly, and if you need to get your calculator, go and get it. I'm also going to show you the steps that I'm doing as I go. So I clicked mode. I should have just done it once. Then I click 3 for table, and I get to this screen here, f of x. Now, if you have a sharp calculator, it's very similar. You go mode 3 table, and it says function 1. And into this function, you're going to put the function that you want to draw. So in this case, it will be sine. Then I go alpha. Then I go the bracket thing, which gives me the x there. And then I close my bracket. And then I go plus 1. And what that is the equation of the graph that I want to draw. Now, the calculator is not done helping me yet. I now need to put in the other information. So how do I do that? Well, I press equals. Okay, now it's asking me, do I want to put a second function in? I don't. So I'm going to hit equals. And where do I want to start? I want to start at 0. Where do I want to end? I want to end at 360. And what is my step size? My step size is going to be 90. And goodness knows, it gives me the points that help me draw this graph. So 0, 1, if I use the scale, let's make it a scale like this. 0, 1 is going to be here. And 92 is going to be here. And then 181 is going to be here. In fact, let me just, before I carry on, let me just ask, give me a thumbs up if you followed what I was doing on the calculator. I'm going to do it again and again in this lesson, but I just want to get a chance to thumbs up if you followed what I did, thumbs down. Okay. I might have lost some of you there. Don't worry, I'm going to do it again now. So don't worry if I've lost you. So I'm going to press down here. So 270, 0. And then I'm going to go 360. And that is, oh, it's 1. It doesn't go down to -1. It goes up to 1 again. So I'm using the calculator to help me get the point. So let me start again. I go mode. And then I'm going to go table. And I'm going to go sine alpha x. So I basically, when I hit alpha, I get the red x. Close that, plus 1. Then I go equals to get to the next start. Then I see where I start is 0, where I end is 360, and my step size is 90. And so now these dots, these little points I've got here, I've put dots here. We are, Camelo, you are allowed to use this in exam, yes. And so what would this graph look like? It just looks like this. Sorry, that should be more curvy over there, that last bit. So, and when we draw trig graphs, we often have to label the turning points. So that would be 92, and we also have to label the endpoints, 361. And when you think about it, all that this plus 1 has done is it's shifted the normal trig graph up by 1. So the normal trig graph would have just been below this, but your calculator's helped you adjust what's going on here. Okay, now, I want you to try and do the same thing, except I want you to draw for me the graph of sine of x minus 1. Okay, so you're going to draw the graph sine of x minus 1, and you're going to draw it for me on the domain 0 to 360. And I want you to try and use your calculators to help you do this. And if there are questions, I really encourage you to ask them. So Kaylee's asked, what is the step size? Okay, Kaylee, for the sine of the cos graph, the step size is just the period divided by 4. If you have the tan graph, the step size is the period divided by 2. So in the one that you're drawing now, the period of the sine graph is 360. So your step size for this one will be 90. So 360 divided by 4. So I'm going to go sine x minus 1. $360, and it is going to be 90. So I get 0 minus 1. Let's do a different color. And we actually have to use we have to push down on the down arrow there. So 270. And then 360 minus 1. And what I like about this, I think a lot of you would understand that what do you think the minus 1 does? It obviously shifts the graph down. And that's, that's great. You can work it out by thinking, okay, where does the sine graph normally go? Just move it down. But the dots, I suppose this just saves you some of the stress. And so if I want to see what this graph looks like, it's just going to look like that. And so if I call this graph, top one is F, and let's call the bottom one G, and this is F, and this is G, and then I could label that point. I could also label this point. Okay, so that's not too bad. Give me a thumbs up if you're feeling okay and you're following what I did there. Give me a thumbs down if you're feeling uncertain. Okay. Fantastic. Take a screenshot if you want, because we're going to now start mixing in another change. So now let's play on a bigger canvas. So what I'm going to do now is I'm going to enlarge it so I have, basically 720 degrees of runway. And I want you to draw for me the graph of y equals 2 cos x. And I want you to do it for me on the domain minus 360 to plus 360. And I'd just like someone to tell me, if they can, what do they think the 2 does to the basic cos graph? What do you think that 2 in front does if I have to compare it to the simple cos graph before you start? Who has an idea about what that 2 might do? It's called a transformation. Almost, what's the opposite of compress? It stretches it upwards. It's called an amplitude change. And so it's almost like it stretches the trig graph upwards and downwards vertically. It stretches it vertically. This is called an amplitude change, whereas the previous one was what we call a vertical shift. But you'll see this in the calculator now when you start to use it. So I'm going to put 2 cos x. But I started minus 360. I end at 360, and my step size is 90. So take some time to plot the points and go through the process of drawing this. And then if there are any questions, I encourage you to ask them as we go about trying to read off. So I suppose we need a scale 1, 2. So minus 360, 2. That's 360, wait, 362. Okay, so now that I have all my dots, to connect them up, you can connect them up. Sorry, that should be a curved graph. And so this is the graph. If I label these points, this would be 180 minus 2. This would be 362. This would be minus 362. This would be that. Bonus question. What is the range of this graph going to be? So what is the range of this cos graph that has been transformed going to be? Pop your answers in the chat or raise your hand and we can talk about that. So Kat has put in an offer. Has anybody else got a similar offer? And Pilo agrees. So yeah, it looks to me like the highest value it gets to is 2. And the lowest value it gets down to is -2. So the range must be between those two. Or if we use interval notation, it would just be like that. Yeah, not so bad. Okay, so the other thing I want to point out is that there are 2 full cycles of the cos graph in this domain. So, and what's happened to the cos graph is it's been stretched up by 2. So now, like, if you go from the position of rest, you go up by 2 units in that way, but you can also come down by 2 units in the other direction. And that's why the range has 4 units of sort of space to play with. Okay, now I know what you want. You want me to combine these 2 things together. And who am I to stand in the way of your progress? So let us draw the graph of y equals 2 sine x minus 1. And I want you to draw this on the domain minus 180 to plus 180. So using the skills that you've learned so far, I want you to draw the graph of 2 sine x minus 1, which seems to have had its amplitude changed to 2, which is a vertical stretch upwards, but there's also been a vertical shift downwards. And the question is, what will the final graph look like when you draw it in the domain minus 180 to plus 180? Over to you guys.
Give it a go, guys.
Here we go. I think students are busy punching furiously on their calculators. They're like, what? How could this calculator be hiding all these secrets? Why have you not revealed it? But it is. It's because it's not just, you can do it using your head, but it just takes some of the processing load off, which is nice.
Definitely.
But yeah, if there are any questions, please do jump in. It's one of the nice things about being live. So I've got, what have I got? 2. Can I go back here? Oh, I can just go back here. 2 sines. Now, what you must do with this question is you must close that bracket. If you don't close that bracket, it thinks that you want to do something else with this. And then, what's my step size? My step size is still going to be 90. So minus 180. Okay, let's make sure my scale is consistent. So this is 1. And this is 2. And minus 180. Minus 90. Oh, I need some extra runway here. So minus 80 minus 1, minus 90 minus 3, 0 minus 1, 180 minus 1, I think I missed, oh, 91. Yeah, I missed something in between. I thought I had. There it is, like that. So this feels yeah, so I basically have those points. So I have that at minus 180, minus 1. I have this at minus 90, minus 3. This point is 91. And this point is 180 minus 1. And then I would also label the function. Okay, now bonus question. What is the range of this particular graph that you've just drawn that has two transformations on it? What is the range for this graph that you've just drawn, this trig graph you've just drawn? So what I like about the graph and all this, I mean, you can see the lowest point is minus 3. And how high does it get? Well, it gets up to 1. And so we could say the range is from minus 3 to 1, if we wanted to use that notation, or we could just say that it was like that. And so the main purpose of tonight's lesson is to get you comfortable drawing trig graphs and also realizing that the changes, like what they mean. So for example, this stretches the graph vertically, this just shifts it up or down, but they can also have two things happening at once. And if that happens, it can start to get a little bit confusing. But another way of thinking about this graph is it's basically the sine graph that went down by 1 unit to get to here. And then instead of being only going up by 1 unit, it's gone up by 2. And the reason it goes up by 2 is because of that 2 in front. All right, I think it's time for a break, a brain break. So what I would like is I would like everybody to be standing. And I want to see your faces. I know lots of you are hiding away today because it's cold and you don't want to be seen, but I'd love to see the warm-up or the brain break.
Please turn on your cameras, guys. Let's see your lovely faces.
Show me your cool winter woolly jerseys and hats and whatever you're wearing to keep yourself warm at this part of the time of the year. Okay, so you know what's coming next. You know what's coming next. So we are going to start by just swinging our arms and not whacking anything or anyone, but just loosening up and shake out the arms, shake out the hands, pretend you're made of rubber, and then pick out your feet, maybe shake your feet around a little bit so the blood flow moves around. And then let us do some arm circles, big arm circles, going into smaller ones, and then change direction into smaller ones, into bigger ones. And just feel your shoulder muscles rotating nicely. And then do whatever relaxes you, but I like doing this, just kind of letting my body rotate a bit. And as I get more relaxed, I see that I can twist further around. And let's just do a little stretch with the triceps. I like this one because when my shoulders hunch forward when I'm in front of the computer, I feel the muscle relaxing. Oh, this is nice. And then other one. Yo. And there we go. Okay, let's get our heart rates up. I don't have jumping jacks in me today, so we're going to do skipping. But if you have a heart rate raising activity and you want to submit it to us, please do let us know. I'm sure we can add another one at some point. But for today, we're going to do 20 virtual skips, which was a suggestion from a student a while ago. So let's go. 2, 3, 7, 8, 9, 10. 16, 17, 18, 19, 20. And then the aerobics part of maths today is over. See if you can do a maths 24 question. So here are your puzzles for the day. choose the one that you think you can go after and pop your suggestions in the chat. Who feels like they can solve the Maths 24 questions today? So Andile has said 2 times 9 plus 5 plus 2. So that would be 18. Are you close, Andile? But no cigar unless no, you get to 25. So you're close, but not quite. Bongokosi has said 8 minus 4 times 7 minus 4, which is correct. Yes, 24. So you're good. Andila has said 8 times 2 plus 5 plus 3. So 16. Yep. So blue is gone. It's only red that needs to be taken. Unfortunately, that's not a 9. This is a 6. This is a 6 because there's a thing at the bottom. Can you get that one? So 6. Yep. Kat, you've got the yellow one as well. So how come the red one's meant to be the easiest? Why is this causing such 6 minus 2 plus or times 5 plus 1. Well done, Nompilo. That was a toughie today. The red one was like the toughest one. So 4 times 6, which gives us 24. And 6 times, yeah, fantastic.
Nicely
Okay,
done,
cool.
guys.
That was a good brain break. Let's go back to our drawing of graphs. Okay, well, I feel like we've neglected tan a little bit. So why don't I give you the following graph to draw? So I want you to draw for me y equals tan x, and I want you to draw it over the domain 0 to 360. And I'll bring my calculator back while you get started on doing that so that I can let me bring back this. Yeah. So can you draw for me the tan graph over this domain? What's my step size going to be? Aha. So you actually, in theory, the step size would be 90, but it's not wrong to make the step size. When you draw it, it would be, but so actually here, you could have put into your calculator step size of 90 or the step size of 45. I think that having a step size of 45 will show you more information. And so probably I'm going to go with that. So let's go with that. 0, then 360. And if I say step size of 45, it's going to give me coordinates every 45 degrees. So, for example, I get 0, 0. Now, what's this error thing? What's going on with this error thing? Yeah, it's the asymptote. Well done, everyone. Okay, so when we're drawing this graph, we know there's going to be asymptotes here. So we have 135 minus 1. So where's 135? Or have I not done this in a nice, neat halfway between? Oh, I've chosen the wrong axes. Let me go and get ones that are nicely divided up like minus 1. Why is this? Oh, I wanted one of the ones like the ones below here. So let me do that on this one here. So if I go 2, and I go I'm rather going to use this one. Can we mute? There might be a I think there's someone who's not on mute or something. There's some background noise, so maybe just check that if you can. And then, so we have 45 and 1. And then we have 90 error minus 135 minus 1. 180 is 0. And then this one is going to be like that. 315 minus 1, which is going to be down here. And then 360 is 0. So what you should have is your tan graph looking something like that. Yeah. And what you see is you don't just get one tan graph, and you actually get one full one, and then you get a half on this side and a half on that side. And it makes sense, because if you didn't have these extra points to fill in, then it would be harder to know where things are going. Give me a thumbs up if you're okay with that. Thumbs down if you are unsure. Then I know I can move on if you are feeling good. Okay. Well, what if I start to make the tan functions a bit more exciting? So how about I say to you, I want you to draw the graph of y equals tan of x minus, no, let's make it plus 1. And I want you to do that on the domain minus 360 to plus 360. Go ahead and see if you can draw that graph. Now, in terms of just logic, this is called a vertical shift upwards by 1 unit. That's what that is doing. But let's see if you can draw that graph for me using the... I think I would use a step size of 45 degrees again, because I want points fairly often here. Turn. I'm going to put my errors in first. So minus 90. And what you then notice is actually these asymptotes have to occur every 180 degrees, because the period of the tan graph is 180. Aha, good question, Ubuntu. What is the range of the tan graph? So the range of the tan graph is actually, it's any real number. So, and the previous one, the same thing. So if you look at the tan graph actually has no restriction on the range. It does have a restriction on the domain. The domain is everything except it cannot be on the asymptote. But the range is unrestricted. With a tan graph, you can go as high as you like and as low as you like. But good questions, everyone. Good questions. Let's see if we can go back to filling in the other points here. So we have minus 360 and 1. So let me put these scales. So wait, minus 361 would be that dot there. Minus 315, 2 would be here. Then I've got the error. I've got minus 225, and that is at 0. Then 180 is at 1. Minus 135 is at 2. And then minus 90 is at error. And that's fine, isn't it? Minus 45 is at 0. Zero is at 1. 45 is at 2. 90 is an error. 135 is 0. 180 is 1. 225 is 2. 315 is 0. Let me try that again. So 315 is 0, and then 360 is 1. Okay, this is quite a bit of drawing here. But what you can see here is you can kind of see the shape of the graph. There's the 1 bit. And then you can kind of see the same thing happening here. And then this one is running out of space. And if you think about what's going on here, the whole graph has just gone up by 1 unit, right? So it used to be that the tan graph would go through here, but now it's going to go up by 1 unit to there. And then the same thing is just repeating in the one over here, and then the one over here, it's the same thing, it's going up there. That was quite a lot of plotting, but I think it's important to see how helpful it can be in dealing with difficult things like this. Give me a thumbs up if you're okay with what I'm doing, thumbs down if you feel confused or uncertain. Just need some feedback. I know it was quite a bit of solo stuff there. Okie dokie, okie dokie. All right, well, let's throw in a couple more because, now you guys are getting quite good at this. So let's draw 2 functions on the same set of axes. I think you're ready for that type of thing. So let us hang in there, Lomix. I encourage you to ask a question now as we go through this. So let's say I want you to draw the graphs of f of x equals minus 2 cos x plus 1, and the graph of g of x equals sine x. Should we make it sine x minus 1? And I want you to do this on the domain minus 360 to plus 360. I think this is probably going to be the last one tonight, or the second last one. I want to see, can you draw this graph for me? These graphs, these 2 trig functions for me, using what we've learned about tonight. It feels to me like this is an amplitude change, although we haven't spoken about what the negative does. It feels like this would shift the graph up by 1, And then this one just seems to be shifted down by 1. The trig graph, a normal sine graph, but just shifted down by 1. What does that look like? Over to you guys. And then Lomix, how can I help you? What do you have a question for me that maybe I could help you with? Or anybody else who has a question? I really do want to use my time effectively here. Okay, can we unmute Lomix there?
Good evening, sir.
Good evening. How can I, what's your question, Lomix?
My question is, it really confuses me on how to draw the lines in the tan graph, you know, because
Okay.
Yes, it really confuses me because I kind of draw the lines incorrectly, and I think it's going to affect me in the long run.
Okay. Can I give you some basics about the tan? The tan has 2 parts. So when I draw my tan graph, I always start by putting in my asymptotes first. And so on your calculator, you'll see that there's like the error signs. Did you see those error signs?
Yes,
okay,
sir.
so what I first do is I get my like field of play. So, and then I know that the tan graph is going to be drawn with 2 halves. Now, the 2 halves are going to start from like the top half. It's almost like a hand reaching up. It's going to get closer and closer, but not quite get there. And then I draw the other one just sort of going the same way, like it's diving down.
So why are we doing this? Like, I don't understand why. Yeah.
Why is the shape like this? Is that what you're saying?
Yes. Yes, sir.
Okay. So the tan graph is a very strange shape because the tan graph is actually the same as the sine graph divided by the cos graph. So there's an identity in trig. Now, that is why the shape is so weird. And whenever cos of x is 0, that's where we get these asymptotes. So if you look at the cos, so that's why we have these funny asymptotes. And and then the other thing is that basically the shape is what it is because it comes from the values of these trig functions. So the shape kind of falls out of the tan relationship. And so you just have to learn how to draw the sort of shape. And the way I think about it is something taking off and something diving down. And I just chop it up into 2 halves.
Okay, thank you, sir.
And just keep practicing. It's weird at first, but your brain kind of gets, I just think of it like this. I think, where am I starting? And I just go up like I'm taking off. And then I just dive down like I'm diving down. And then I just repeat.
So my question is, you know, the way we drew in negative 360, the line was a bit shorter, you know?
Yes.
And then now, as soon as we got to 180, the line becomes, we have to start, the line becomes more longer. Why?
Yeah.
That's the thing I don't understand now.
Okay, so we are choosing to only look at part of the region. And so because we're only looking at a certain collection there, and so because of that, it's almost like this got cut off. There was a piece here that never gets shown, but because we ran out of time here, that's why you don't see that next bit, because you ran out of runway.
Thank you, sir. Thank you very much, sir.
Pleasure. All right. Let's have a look at drawing this shape here. So I'm going to use my calculator. So I'm going to go computation. Oh, wait, not computation. I'm going to go table, and I'm going to go -2 cos x plus 1. And I'm going to get -360 equals then to +360. Oh, wait, did I go back? Go back. So I don't want -360. I want to blank that out. And I'm going to go equals. So I start at -360, then +360. And the step size is going to be 90. And so I get minus 360. Let's go 1, 2, 2. So minus 360 minus 1. Minus 271. Minus 183. So I actually need a bit more room there. So I've got minus 180 and it's 3. Minus 90 and I've got 1. I've got 0, minus 1. Oh wait, no, it's going to be here. I've got 90 and then 1. 180 is 3. Oh, this is quite a big one. 270 back down to 1. And then 360 back down to minus 1. So F, which is a cos graph, is going to be looking something like that. So that will be the graph of F. So Nakazumolo has said, how do we know the steps to plot the graph? How do we know whether to use step 45 for a tan graph or step 90? So it actually doesn't, all the step size tells you is how many points. If your step size is smaller, you get more points. So it's not wrong to use either step size. It's just a case of which one, how many do you need? So in this case, I chose a step size of 90 because that's all I needed to see the shape. Whereas with the tan graph, I needed a smaller step size because I wanted more points to see the shape. That's basically all I did. Okay, let's just do this last bit here now. So let's go to mode, table, and then let me put in there sine of x. Oh, wait, sine of x, close brackets, minus 1. And I'm going to start at minus 360. Wait, let me go back here. So I'm going to do this out of my own thing. So I know that the sine graph would now go between basically here and here. Right? So the reason is the whole graph is just shifted down by 1 unit. And if that's the case, I'm just going to draw this from my memory. All I know is that the graph is going to look like that. And over here, now again, I've just put those red lines to show you that I know that the range for this basically has gone, it used to be between minus 1 and 1. It's now between 0 and minus 2. And that's all that happened. All right. In the next, so we've done quite a lot tonight. I'm going to stop there for now. The focus tonight was on amplitude changes. So amplitude changes and vertical shifts. And using our calculators, we can see that basically the amplitude is stretching it up or down. And the vertical shift is simply moving it up or down by a certain amount. In the next lesson, we're going to talk about period changes, if you change the period of the graph. And also we'll talk about horizontal shifts, but we'll still use our calculators like we did today. Okay, that was a lot for one day.